Yeah, good morning to all of you. So in the finite fields, what is a field we discussed? Then, so F is a field, then Fx is a PID, set of all polynomials over it, right? Then, so Kronecker given one thing that F is a finite field and Fx is a irreducible polynomial. Then there exists an extension field over which contains the root of f of x, right? And F is clearly contained, but of course isomorphic copy of this field. So Lagrange proved that if F is a field, then if I take any polynomial fx over fx, then it has at most n roots in, right? This proved by induction. Okay, so then we defined what is a characteristic of a ring, right? Then we showed that the characteristic of an integral domain is either 0 or a prime number. Then we proved that characteristic of finite field is always a prime number because it is an integral domain and it has a characteristic greater than 0, right? So that because of that, it is a prime only. And then once we have that, then every finite field contains a subfield isomorphic to ZP. Then F is an extension over ZP. Then F is a vector space over ZP, right? Then once it is a vector space over ZP, then it has a finite basis, right? So it has a finite basis. So that we are calling as alpha 1, alpha 2, alpha n, right? Yeah. Yeah. Okay. So then if I take any element x in F, then x is equal to a1 alpha 1, a2 alpha 2 up to a n alpha n, where a belongs to ZP. So each element A has p choices. So mod F also p power n elements, right? So then with that we proved already that if I have a finite field, then it has p power n elements. Yeah, every finite field has p power n elements. So can somebody tell me, is there exist a finite field with 6 elements? Hello? Is there exist a finite field with 6 elements? Okay, so it does not exist because 6 has 2 prime divisors, right? Hope I am audible, right? At least. Okay. Hello?
Yes, sir, you're audible.
Okay. Yeah. So from where this P comes from, it is a characteristic, and where this N comes from, that is the number of elements in the basis, right? So we discussed another way to look at finite field has P power n elements. How do you prove it? So we showed that first characteristic of F equal to P. Then we need to show that finite field has P power n elements. How we proved it? First of all, every field contains at least 2 elements, 0 and 1. So cardinality of F is greater than 1, right? Then there exists a, suppose there exists another prime. If there exists a prime which divides order of F, then I claim that Q actually equal to P only, and this is the only. Okay, first of all, characteristic of F equal to P, then P into 1 equal to 0, right? Because that implies order of 1 equal to P, and P divides order of F. This we know. Order of element divides order of the group. Now suppose Q is another prime such that Q not equal to P and Q divides order of F, suppose. Then by Cauchy's theorem, so there exists an element x in F such that Q dot x equal to 0, because F is a field. See here, F is a group with respect to addition. So P into x equal to 0 and Q into x is also 0. But if since P and Q are distinct primes, there exists M and N such that Pm plus Qn equal to 1. So that means that so x equal to 0 only. That means that our assumption that Q is another prime dividing the order of is false. That means so P is only prime dividing order of F. But order of F contains at least 2 elements. Because that means it has a prime divisor. But P is the only prime divisor. Then the number of elements equal to order will be of the P power n for some n. But in the second proof, we do not know what is n. It is only there exists an n, right? Okay. Then later we proved that this theorem that f is a finite field, then f minus 0 multiplication is a cyclic group. So before that, I just noted one thing that f plus need not be a cyclic group. Okay, but f multiplication is a cyclic group. We remember that. In fact, f as a group with respect to addition, it is isomorphic to Zp cross Zp cross Zp. Because characteristic is p, every non-zero element has order p. Yeah, so that part we discussed, right? But whereas f minus 0, if you prove that if you remove 0, it is a cyclic group, then it has exactly isomorphic to Zp power n minus 1. So what is the strategy? Strategy is that we took m is equal to maximum of all orders. Okay, we claim that m equal to q minus 1. To prove that one, we used some results in uh, group theory. We completed it. Yeah. So this is what we done in the previous class. Okay. So what is the conclusion? Finally, what is that we proved in the previous class? We proved that if f is a finite field, okay, then it is which is of whose order number of elements in equal to p power n. But we not proved that for every p, every n, there exists a finite field of that order. Exist we not prove. So what we proved is only this. So f is a finite field. So there is a problem with my video today. So I cannot show video. So let f be, if f is a finite field, okay, then order of f equal to p power n for some prime p, and n belong to n. So is there any doubts in this? Are there any doubts here? Okay, good. This is one thing, and later we proved that this is what I'm just concluding what we done in the previous class. This f minus 0 with respect to multiplication is a cyclic group. These two things we done, right? Yeah. So now once f minus 0 is cyclic group, is a cyclic group, then what is going to happen? This f minus 0 is equal to, in fact, this f is equal to now. So it can be written as 0 alpha alpha square. Can you somebody help me? Yeah. I'm assuming that the field it contains p power n elements.
Alpha power
Alpha power
p power n minus 1.
p power n minus. So p power n power minus 1. Yeah, alpha power p power n minus 1. So because the order of this this f minus 0 order of this group is p power n minus 1. Because order of f is p power n. If I remove 0, order of this is p power n minus 1. And it is cyclic group, then f is a generator. So then entire f now I can write very beautifully. Real numbers, complex numbers, Q, I cannot write this beautifully, right? All elements in F now powers of element. That is the thing. This alpha is called primitive root, primitive element. Alpha is called primitive element. So how many primitive elements are there?
Phi of p power n minus 1.
Yeah, so we know this, right? Phi of p power n minus 1, because number of generators equal to phi of n, right, in a cyclic group. Okay, so we have this many. It is not unique. Yeah. So this much we done. Mm, So now we'll go move further. Okay. So all are going to be logical. So there is a third proof also. So but I'll give sketch of that. Okay. So let F be a finite field. Okay. Then it has p power n elements. See, for proof one is that proof by field extensions. Extension I proved. Second by using the group theory, right? The Cauchy's theorem. Third proof we can prove that F is a finite field. It has p power n elements by suppose that this is a very interesting proof. Okay, so you take alpha 1 belong to F minus 0, right? Then I take this alpha 1 1 into alpha 2 into alpha 1 0 से शुरू करता हूँ. So 2 into alpha 1 3 into alpha 1 I can go so that they are all distinct. So F has characteristic P, right? So if it is characteristic P, so after some time it is P minus 1 into alpha 1. Afterwards it becomes 0, right? Right? Yeah. So so this is subset of what now? At least can you say this?
F.
It is a subset of F, right? If my F equal to this, then what happens? If F equal to this set, right? Then what is the cardinality of F, please?
P.
P. So we are done, right? This way the proof goes this way. It is a proper subset, okay? So this 0 alpha 1, 2 alpha 1 and so on, P minus alpha 1. So here 2 alpha 1 means alpha 1 plus alpha 1. If it is a proper subset, then what is going to happen? There exists alpha 2 belong to, so let us call this set as S, right? So then I have, so there exists an S element alpha 2 belong to F minus S, correct? Yeah. Now, what is the type now I do? I'll construct, this is, let us call this as S1, okay? Yeah. Now I'll construct S2. How I construct it? So, so it is same as that, but just I'm giving, so I'll take it A1 alpha 1 plus A2 alpha 2, right? Where A belong to, so the S1 also you can see, S1 is also, you can see that S1 is in fact equal to A1 alpha 1, right? A1 belong to F, right? Z2, right? Yeah, so this A belong to Z2, right? Then again you can show that no two elements in first one is that I am giving it an exercise. No two elements, no two elements in S2. Sorry, it is my satisfaction only. I am telling the different proofs, but one proof is sufficient. No two elements in S2 are equal. Okay, first prove that. Okay, once you prove that one, then what is the cardinality of S2, please?
P square.
So if my F is equal to this, we are done. I hope you understand how we proceed. Otherwise, we'll continue. We continue, and why it will stop, this process will stop.
Has only finitely many elements.
We stop as F contains finitely many elements. Yeah. Okay. So okay. Still again I'm conclude we only proved that f contains p power n elements and f minus 0 with respect to multiplication is cyclic. Okay, this much only we proved. Now I'll just state few things, right? Okay, so this is easy, but if alpha belongs to f implies alpha power q power n minus alpha is equal to 0. Is it true? Finite field with e power n elements. Are you able to prove this?
What is Q?
Yo, sorry. Go on. Yes, sir. Thanks. So think about all of you.
Yes, sir.
The question is that if f is a finite field, right? In particular, so in future, what we do is that I'll write f contains q elements. Now q is equal to p power n for some n, right? Yeah, how to prove it? This one of you. I'll write here further. Let f be a finite field with q elements, right? F be a finite field with q elements. Then for every alpha belong to f, alpha power q is equal to alpha. Okay, is the statement clear? Is it not like Fermat's-Little theorem? In the Fermat's-Little theorem also, x power p equal to x, you remember, right? But now we are extending it much better. Yeah. Yeah. Somebody give the proof now. Quickly.
If alpha is equal to 0, then it is true.
Okay. Well, thanks. Yeah. So suppose, yeah, proof. Okay, proof. I'm writing the proof. Proof. If alpha is equal to 0, implies alpha power q equal to alpha is true. Correct. Very good. If alpha not equal to 0, yeah, this implies alpha belong to fq minus 0. Yeah, correct. Now, yeah, I know that what is that you want to say. So now fq is this fq minus 0 is a group. Is group with respect to multiplication. Okay, and then automatically alpha power fq minus 0, right, is equal to 1, right? So this is alpha power q minus 1 is equal. So this implies alpha power q is equal to alpha. It does not require that it is cyclic and group is sufficient, right? By Lagrange's theorem. Okay. So is it okay, Achila? Sorry
Yes,
for
sir.
asking by name. Okay.
Yes.
Yeah. Okay. Good. So very simple, but I'll give one proof that we done for since we done number theory course. Better to have one more proof since they're very simple and easy. What is that I do? Again, alpha equal to 0, we are done. We are done. Okay. If alpha not equal to 0, what I do is that so I'll multiply alpha to alpha into so this f minus 0 contains elements, say alpha 1, alpha 2 up to alpha q minus 1, right? These are all the elements. Now I can multiply alpha to all of them, right? Alpha times alpha 1, alpha times alpha 2, and so on, right? Alpha times alpha q minus 1. These are also elements in fq minus 0, and they are distinct. Right? They are distinct easy. In the group, we have that property. In a group, you multiply alpha element of the group, element of a group to all the elements, and they are all distinct by cancellation. You know that they are all distinct. Yeah. Then what I do, I am giving the proof. I am recalling that how we proved Fermat's little theorem or Euler's theorem. Yeah. So this is not about using the Lagrange's theorem, right? So this product I am taking, right? So alpha times alpha q minus 1, right? Which is equal to, so why I wrote alpha 1, alpha 2, alpha q minus 1, one element is 0, that I not took, okay? So this is actually equal to alpha 1, 2 times alpha q minus 1 only. So this implies alpha power q minus 1 is equal to 1 by cancellation. Is it okay? Another proof. Yeah. Okay. So if you have any doubt, let me know. Okay. So what is we done today till now? We proved that if F is a finite field with Q elements, then every alpha satisfies this equation. F is a finite field with Q elements, but remember that Q equal to P power n for some prime and some n always. Yeah. So we can replace this with P power alpha power P power n equal to alpha. Yeah. Okay, good. I hope no questions, no doubts. Now I will give another one. We denote now onwards. We denote field with p elements where p is prime. As fp. Of course, you know it is equal to zp, but I am denoting now onwards fp. Okay, okay, because everything I am denoting by fq now. So, but notation I'll give further. So once you are giving some notation, that should be unique. There is a unique field of that order, then only. That's why I'm not done, but still I'm using. Yeah. So anyhow, I'll prove it today. We done. We denote what is we done. We denote. Yeah. Okay. Okay. Now a small result. Let F be a finite field. With Q equal to P power n elements. Okay. Then F is isomorphic to F of x by f of x, where f of x is an irreducible polynomial. Polynomial of degree n over fp. Are you okay? Are you clear? Is the state clear? Hello.
Yes, sir.
I'm telling that how actually that field look like. So these are existential theorems. So we proved that if I have a finite field, then it has p power n elements. Okay, but can I? How do I see the elements in that? ZP I know how elements in FP look like, but in general, power n पे कैसे दिखेंगे? Right? There is a question, right? So to answer that one, this theorem will help little bit. At least the way I can represent. So FP of x by ideal generated by fx, where fx is irreducible polynomial of degree n over fp. Yeah, and somebody giving the proof of this.
You can explicitly write down the elements in the quotient field.
Okay, so let f is equal to 0 alpha alpha square alpha power q minus 1. Yeah, yeah, right. This is one way, but here this is correct. This is one way to write field. What is
That
alpha
is
here? I'm sorry. Yeah, alpha is a generator. Yeah. This is one way, but here again we don't know what is alpha, but it is again theoretical. So yeah, this is one way to write. Yeah, but what something please.
no. So
See, my
we
goal
can
is
take the
this.
basis for f.
Okay, but I want to show that this isomorphic this FC of okay, you are telling that you take a basis, so but how do you get irreducible polynomial? I understand what you are saying. You take a basis, then you take more than that number of elements, then they are linearly dependent. That way.
Yes.
Okay, good. But what is that I want to say this? Since we know that we proved whatever we proved, we are using. Since f minus 0 multiplication is a cyclic. This implies there exists alpha belong to f minus 0 dot and is a generator. Is a generator. Right? See, you know how do you prove this? This will help you. R of x quotient by x square plus 1 is isomorphic to what?
See.
C. But how do you prove this result? The same we are imitating. Yeah, how we prove here? We are imitating the same.
Map x bar to I.
Ah, yes, exactly. So what is that we do? X bar instead of the, okay, you are correct. What is that I do? I take FP.
So we can like define map from fpx to f by x going to
Yeah,
f of
exactly.
f of alpha.
Exactly. Yeah. So we are taking, please remember, all of you be careful. F is a finite field with p power n elements. Then what is that I'm claiming? F is isomorphic to Fp of x by some irreducible polynomial generated by irreducible polynomial. Right? So to prove that one, I'm defining a map f of x to f. Okay, how I'm mapping? So x is an evaluation map. X going to alpha. Okay, evaluation map. Okay, in particular, I'm calling this as some phi alpha of x. Okay, so phi alpha of x is equal to alpha. Right? Is it a homomorphism? Is P alpha a homomorphism?
Yes, sir.
So when I done a mistake. No, yeah, I done a mistake. Yeah, mistake I done. Better I say like this way, then it will be advantage. Yeah. This will take care, but better like this. It will take f of x to f of alpha, right? Why this is an element in f? Yeah? Why this is an element in f, right? So ask questions so that it will be easy for you. Since yeah, what is f? F is a polynomial in with coefficients fp in zp, but fp is a subfield of f. So all the coefficients of f are in f. Alpha is already in f. If I put alpha in there, so it is in f, right? Yeah. So I answered it. I hope there is no problem. Now, what is phi of alpha of zero polynomial, right? Phi of alpha of zero polynomial is so zero of alpha, right? Zero of alpha. So it is equal to zero. Okay, that is one thing. So now we take it, yeah, so f of x plus g of x, right? So it is equal to f of alpha plus g of alpha. So which is equal to p alpha of f of x plus p alpha of g of x. So this part is okay. Similarly, multiplication is also easy to check, right? So similarly, p alpha of fx into gx is equal to p alpha of fx into p alpha of gx. Yeah, so this much is okay. So it is a homomorphism. Implies p alpha is a homomorphism. Okay, now what is the next question? Is p alpha is onto question? Can somebody help me? P alpha is defined like this.
Yes, sir.
Now, elements in F look like 0 alpha alpha square and so on. So if I take y in if I take let y belong to F, right? How will it look like? Y is equal to, of course, 0 minus 0. Already 0 is there, I know it. So I'm taking non-zero element so that it will be easy. Yeah, so you can go down, yeah, tell. Even I write little fast.
There exists some cases that
Uh,
y equal to alpha power k.
Right, where exist k belong to n such that I is equal to alpha power k. Yeah. So now, what is that phi alpha of something equal to alpha power k? What is that? What is that
X power
polynomial
k.
which takes
X power k.
x power? Yes. Okay, this guy is, I'm right here, x power k. So that you are, so I answered this question and you told the answer. So fp of power k equal to this. Now, so now finally we proved that this p alpha is p alpha from fp of x to fx. F is an epimorphism. Don't worry if you do not know. Epimorphism is onto and homomorphism, right? So then by fundamental theorem of homomorphism of things. Yeah. So what is that we have? So fp of x. Yeah, somebody else instead of Amir. Fundamental theorem of homomorphism means what we say onto map homomorphism onto. Can somebody help me?
F by kernel of this map.
Kernel of this map phi alpha is isomorphic to F,
Isomorphic
right?
to F. Yeah.
But now you know that F is what? But F is a field. Right? If F is a field, then what do you know about this kernel of P alpha? Right? I don't need to write. Sorry, yeah? Sorry. So kernel of P alpha is
Maximal idea.
it is a maximal idea. And further, this FP is FP of X is PID, right? F is field, then FP of X is PID. This implies, so my kernel of P alpha is equal to Fx for some X. Right? Moreover, I can take as a uniqueness, we can choose F as F is a monic polynomial. Yeah, so I hope this part is okay. Right? Now, if the so, but we know that this FP of X, FP of X by this. Okay, what is the cardinality of this, right? How it look like? Okay, so actually we know that FP of X ideal generated by FP of X ideal generated by F of X is looks like all elements here look like A0 plus A1X and so on plus AN minus 1 X power n minus 1. Of course, in particular, strictly speaking, I have to write this also I plus X plus I, right? But generally people not write this, okay? Because that this A's are belong to F, correct? FP. So then what is the cardinality?
P power n.
P power n, right? So of course, it is the other way. So if F has P power n element, then my degree. So here, here, here n equal to degree of F. Right? That way we can bring that first F has P power n elements. I can show that degree of F equal to n itself. Right? I hope that those are fine now. Okay. So again, recall what is that we done two things today. First, we proved that this result, if F is a finite field with Q elements, alpha satisfies this equation. That is very straightforward too. Second thing, we proved that if F is a finite field with Q elements or P power n elements, then F is isomorphic to Fp of X by X. So then, if you're able to prove that there is for every n, there exists an irreducible polynomial of degree n, I am done. Then there exists a finite field with P power n elements. But how to prove that? Is there any other way? So now we'll go without actually showing existence. We are proving if it exists, how it look like. Till now, वही हो रहा है. Yeah, अभी तक we not proved. Okay. So now what we do? In the field, from field theory, I will take one particular thing. Okay. In the field theory, one fact I am taking. Okay. What is that? So let F be a field. Okay. Right. And Fx belong to Fx. Right. Then there exists a unique, yeah, splitting field. Splitting field for Fx over F. Is it okay? Is it clear? What is splitting field? Do you know?
Yes, sir.
Can you define?
The smallest field extension of F in which F splits completely.
It contains all the roots. Okay, correct. For example, to make you help you, so for example, my f is equal to q, right? And I take to my polynomial as x square minus 2. Simple example I'm starting with, right? And you know that this is irreducible polynomial. It does not split here. See, by the way, I'm not told fx is irreducible, right? Yeah. So any polynomial that will work. But now I'm taking this x power x square minus 2. Okay, right. So now what is that happening is that there exists a unique splitting field. Okay. So what we will do, we will take this q of x ideal generated by x square minus 2. Yeah, this is isomorphic to q root 2. Again, how we prove this part? See, I do not know this, but what is it actually happening is that I take q of x. I know some bigger complex numbers I know, right? Complex numbers is like a very nice thing which we have. So I will map again my fx to f root. So fx to f root. Again, you can check that this map is homomorphism and all. And then again, onto also we can prove. Onto, not onto, but so be careful, not onto. This mm, what is it I want to say? This I mean, if I confine to polynomials in root 2, okay. So this q root 2. So q root 2 is contained in C. Yeah. So, but q root 2, if you confine to q root 2, then it is onto. Yeah. But this v itself we don't know, so don't worry about that. So image actually. So by so q of x by x square minus 2 is isomorphic to image of this map, this phi. So phi of q of x. Yeah, that is equal to those substituting root 2. Okay, so that is exactly q root. And we know that its degree, it is an extension, final field extension for degree 2. So it is an extension degree 2. Sorry. Yeah. So now what is the splitting field for this one now?
Q adjoin root 2.
1 unit. Yeah. You can see. Yeah. Is it visible? Code is visible?
Yes, sir.
Okay. Yeah. So this now this q root 2 contains both the roots. See, I told you earlier, Kronecker told that you take any polynomial, there exists a field which contains. So he exactly done this, right? But this is isomorphic to q root 2, just I'm telling you. Q root 2 contains both the roots of x square minus 2. So this is the splitting field. Splitting field of x square minus 2, right? So this is a field and which contains both the roots of x square minus 2, right? So what is the splitting field of what is the splitting field? subfield of x square minus x cube minus 2 belong to qx. Can somebody help me?
Q adjoin cube root of 2 comma omega.
So here q of adjoining omega comma cube root of 2. So this is a bigger field. See, we have q of, so it is like this. So here be careful. So here Kronecker part, be careful. See this by x cube minus 2. This is isomorphic to q of cube root of 2. Right? It is also isomorphic to q of omega of cube root of 2. Right? It is also isomorphic to q of omega square of cube root of 2. Yeah? But these fields are called conjugate fields. They are not equal but isomorphic. Yeah, this is the place you can understand much better. But whereas here you see that in this case x square minus 2 q root 2 is equal to q of minus root 2. They are exactly equal, but here they are not equal. Okay, why these two are not equal?
One of them is a subfield of real numbers and the other one is not.
The other one is not. So cube root of 2 is not equal to omega of cube root of 2. Yeah? In particular, what is the degree, what is the intersection of them? Yeah, can somebody help me? This is only Q, right? Yeah. So this is a real field. Subfield of real field. Okay. Otherwise, we may not simple. This is subfield of real field. It is a subfield of X, but not subfield of real. Yeah. Okay. So these are not equal. So what is happening here is that this q root q of cube root of 2 does not contain all the roots of x cube minus 2. So what is the smallest field containing all the roots of this one? Of course, see, complex numbers also contains, but we do not go up to that extent. So the splitting, so by adjoining this part, okay, so q of omega comma cube root of 2 is equal to q of omega of cube root of 2. Yeah? Adjoining this to this, right? So what is actually going on here? So this example may help you later. So we have q, we have degree to extension, q of omega square, and the q of cube root of 2. Okay, but here degree of extension is 2, here degree of extension is 2, here degree of extension is 3. These two are equal. If these two are equal, yes, they are equal. Okay, so I no need to write this. Okay, no? So what is omega here? Omega is equal to root of x square plus x plus. Yeah. Now, yeah. So degree 3 extension, and here this is now subfield of q of omega cube root of 2. and this also subfield of this. Now degree of the extension is 3 here, degree of extension is 2 here. And this is a splitting field. It contains all the roots of x cube minus 2. Yeah. So that is the still now part. Splitting field means now I am taking this. Okay. Now let P be a prime number. Then what I do is that now I'm looking that I'm collecting the set. My set equal to okay all alpha, but belongs to where? Yeah, from all alpha, such that alpha is root of alpha power p power n minus alpha. Yeah. So is the set clear to you? Hello.
Yes.
Okay. So let P be a prime number, and we took this. Okay. Okay. So is it S is non-empty?
Yes, sir.
Why it is non-empty?
Contains 0.
Yeah. So 0 belong to S, and is it 1 belong to S? Yes, right. So S is non-empty. So non-empty is clear. Okay. Now, but before that, be careful that we are doing all operations. Okay. So first of all, okay, let us go like this. Then x power p power n minus x. This belongs to fp of x. Are you okay with that?
Yes, sir.
Now we know that yeah. Okay. Okay. Yeah. So I'm not told here properly. I will now explain. So let P be a prime number, and P be a prime number, and n belong to n. Yeah. So then this x power p power n minus x belong to fp of x. Zp of x. Fp Zp same. Okay. Yeah. This implies there exists a field, yeah, which is splitting field. Splitting field for x power p power n minus x. So this existence I already assumed. Okay. This is the only thing I'm assuming. I wrote here. So let f be a field and fx belong to fx. There exists a unique splitting field of fx over f. Yeah. So now I'm taking this alpha belong to f here. Okay. Alpha is a root. So there is a field there is a field which contains the roots of, we can say like that, right? There is a field which contains roots of this. So no problem here. Now here, okay, fine. Now this is non-empty, is okay. Yeah. So now I'll take two elements. So let us take alpha comma beta belong to S. Okay, what is the meaning of this? Yes, please. Set is clear, right?
Alpha and beta are roots of that polynomial.
So that means that alpha power p power n minus p is equal to 0 or equal to alpha. And the beta power p power n is equal to beta. Okay. Now, can you guess what is my next question?
Alpha plus beta and alpha into beta.
Is alpha plus beta belong to us?
Yes, sir.
Alpha into beta belong to us? This is the question, right? So let us go slowly. So first of all, I think this part is okay, correct? Alpha beta whole power p power n is equal to how much? Right? This part is very easy. Yeah? So this is equal to alpha power p power n into beta power p power n, because in the field is an abelian group, right? So this implies that. So please try to understand here. So this S is now my S is subset of F. Okay, what is F? F is a field. There is a field which contains the roots of x power p power n minus x. What is this polynomial? This is a polynomial f p of x. What is this p? P is a prime number. What is an n is a natural number. And what is S? S is subset of F. Yeah. So now, so this is equal to alpha times beta. So this is true. This part is true. Yeah. Now coming to this alpha plus beta. So what is that I have to do? Alpha plus beta whole power p power n. What is that I have to show?
Is equal to alpha plus beta.
Is equal to alpha plus beta. This is what I have to show. Yeah. Do it. Okay, so let us go slowly, maybe. So we can prove an induction. So first of all, alpha plus beta whole power p equal, right? Is alpha power p plus, yeah, alpha power p plus p times alpha power p minus 1 beta plus and so on plus, right? So p times alpha times beta power p minus 1 plus beta power p, correct? But we are working over fp. Okay, so in this field, what is the characteristic? Characteristic is p. What is going to happen to these things? What is this happens now? This is equal to 0. All these are equal to 0, right? Only this guy and this guy will be left. So it is equal to alpha power p plus beta power p, right? Is it okay?
Yes, sir.
Yeah, we done it actually. See, p is a prime number. P is a prime number. Then p divides p choose I. Okay. I not equal to 0 p. Yes, so these are all 0 because alpha power p plus beta power p. Beautiful part. Okay. In particular, it will give you much better. I will tell that part also. But how do you prove that alpha plus beta whole power p power n equal to alpha plus beta? this and not proved this part. Yeah. Can somebody come up?
Can't we directly just say that if P is prime, then P does not divide, sorry, P divides P power n choose I.
Okay, right. So what is that you are telling is that alpha plus beta whole power P power n is equal to, so alpha plus beta mm, power P minus 1, right?
No. So before, like earlier, we wrote that if P is a prime number, then P divides P choose I. So we can just replace it by P power n choose I. I think that even that result is true.
Oh, right. Okay. Yeah. Okay. So that is also correct. That is another way. Correct. Yeah. So that is way. Other this way is also right. So this way also we can work out inductively. You can prove it that this works. Yeah. So I hope it is clear. This is equal to, you can show. Otherwise, take as an exercise and try. So it is actually in fact this. So it is equal to alpha plus beta, right? So exercise. So please go take it. Yeah. So we proved that. What is that we done? Okay. What is that we done here? We done that this S actually now what happened? It is closed with respect to multiplication and closed with respect to addition, and it is a subset of F. Then say something. And is it necessary for me to prove exist of inverse and all? H is a subset of a group G, where G is finite, where G is a finite group. Then H is subgroup. Can you somebody tell me the result? For non-leave. Yeah.
Just closed under.
Closed under. That's sufficient, right? For every A comma B, which A into B belong to. Closure property is sufficient if my G is finite. Here I am working the finite field, so F is finite field and all, right? So, right. So now this otherwise you can prove, right? Inverse also all that. So now X is a finite field. How many elements are there? Yes. So it is P power n, right? How to prove it is P power n?
That is by Lagrange theorem.
That is okay, but what is S actually? S is a set of all roots of this polynomial, right? S is collection of all the roots of this polynomial, correct? That is the way I defined S. S is all the root of this, right? Set of all the roots of x power p power n minus x. But why these are all distinct? That is
take the derivative.
Derivative. If this is this, then f dash of x equal to, right? So p power into p power n minus 1, right? But this is 0 because of the characteristic. So it is equal to minus 1. So f of x cd of x comma f dash of x is equal to 1. This means all the roots are distinct, right? Yeah, and finally, so actually now we showed that the set S is now a finite field with the p power n elements exactly. So existence is done, but we'll prove much more. Suppose now suppose F is a finite field with p power n elements. And then so implies F is ending as yeah, right? Yeah, that is okay. So then what is F actually? We know F is equal to 0 alpha square and so on alpha power p power n minus 1, correct? But these are all the roots of which polynomial we already done. These are x power p power n minus x only, right? Including 0. Earlier we showed that this alpha square up to alpha, these elements. So right, we done that earlier. All the non-zero elements satisfy the equation x power q minus 1 equal to 1, right? Yeah. So every element in satisfy this equation, right? So my equal to p power n. Right? So we do it. So because that what is that we are telling that this what is this f now? F is a finite field with p power n element. Then what is f now? F is yeah. Can somebody tell?
Consider the splitting field of x power p power n.
Splitting field. Splitting field x power p power n minus x. Because of that, there exists a unique field. Every field with p power n elements is splitting field, but splitting field is unique. So one result I am taking from the field theory without proving. That takes more time. Huh? Sorry for that. So, but the splitting field is unique. So this implies uh, exist there exists unique field with p power n elements. Yeah. So that's why notation came, but we are already started using. So we denote field with p power n elements as fp power n notation because of uniqueness. Of course, uniqueness up to isomorphism. So, any questions till now? Yeah. Are there any questions? No questions, right? Yeah. Okay. So not only existence, that is uniquely proved. So that's why we denoting. Be careful. Be careful. And if I do mistake, also please let me know whenever. F p power n and f p power n are different. Are you following that? Okay. What is the difference between these two? F p power n is finite field with p power n elements. What is this FP power n?
FP cross FP cross.
FP, so okay, it is FP cross FP cross FP. So, but both are now. What do you know about both? Some common thing about these two.
Isomorphic as additive groups.
Isomorphic as
Additive groups.
additive groups. That is one thing. Wonderful. They're isomorphic as additive groups. Can you tell me they are isomorphic in other way also? One more approach.
As FP vector spaces.
Vector spaces, yes, as additive groups. Yeah, very nicely you tell. So additive groups also as a vector spaces. Why I am telling this? Okay? Why I am telling this? Also as vector spaces over FP. See, vector space does not demand multiplication. Okay, now I can bring the multiplication here. So that you remember that in the previous class I told you, R cross R. So R cross R, we need to define multiplication in such a way that becomes a field. It is possible. Yeah. If you just multiply component wise, it is not, but there is a way. So like that. So now this is isomorphic to this. So I can bring here also multiplication. I can bring multiplication and becomes a field. Is it not beautiful? Then what is the advantage? I can think of elements in F power P, Fp power n also as ordered pairs, ordered tuples, ordered n-tuples. So that's why there are various ways. Okay, see, Fp power n is actually what? It is isomorphic to f of Fp of x by some polynomial, irreducible polynomial. That is one way. Other way is that Fp power n is a finite field. So it is a, if I remove 0 from it, then it is cyclic group. So it is a primitive element. So I can write it in powers of alphas. That is another way. Third approach is that it is isomorphic to Fp power n. So I can think of elements of Fp power n as ordered tuples also. Are you okay? Are you fine? It is very nice, but many people not tell those things. And it takes time also to understand those. So while you are writing composition table, so there are more than one way first to express elements in Fp power n, right? So also multiplication becomes easy when you think Fp power n as a cyclic group and as a generator. Their multiplication becomes easy than ordered tuples. Addition becomes easy when ordered tuples. So these are if and so people use the benefit of all these. Is it okay, Amia?
Yes, sir.
Yeah, good, nice. Maybe you are already familiar with, but yeah. So so till now things are fine. So so you are clear with what are these, right? And see, but in our course, my Fp power n itself is equal to F cube, right? This is my alphabet in coding theory. This is my alphabet. Now I will code is a subset of F cube power n again. Now it itself is a field now. Okay. Yeah. So that much is there now. It is a vector space. It is only vector space over that. Okay. What else I want to tell you now? Yeah. Take some small break and again I'll continue. Right. Okay. So till now we are fine. So let us work out some certain things. So let us take my p is equal to 2, right? And compute this of x. Okay. So can you give me some irreducible polynomials? Right? So we'll try to collect some irreducible polynomials. Over f2 of x. Okay, this is the top right now. It's some time. Okay, irreducible polynomials over f2 of x. So first degree 1. Can you give somebody give me degree 1 polynomials which are irreducible?
X plus 1.
Yeah. How many are there? X comma x plus 1, right? Degree 2. What is the product of these two? X into x minus. So x square minus 1, right? X square minus x. Yeah, please remember that x square minus x is actually what? So the roots of this polynomial, this is exactly f2. Right? If I collect the roots of these polynomials, that is exactly f2, right? Yeah, so here 2 power 1, 2 power 1, and here power 1, 2 power 1, right? Yeah, so think of that. Yeah, so now can you tell me second degree 2 polynomials?
No irreducible polynomials.
Yeah,
There are no irreducible polynomials.
no irreducible polynomials of degree 2. Okay, first of all, how a polynomial of degree 2 like a0 plus a1x plus a2x square.
Oh, so x square plus x plus 1.
Yeah, where ai belong to f2. Correct. First write down all the polynomials so that it will be, you are correct, your answer is correct, but let us write down. So the polynomials are, so I'm writing all the polynomials of degree 2 or even 1, all polynomials degree 2 and degree 1 directly at a time. Yeah, so this is, so so a2 equal to 0, right? So a1 is also 0, then it is 0 is one thing, 1 is one thing. Yeah. But anyhow, so only write degree 2 polynomials, but that is better. Yeah, degree 2 polynomials. Okay, so that means that a2 has to be 1. So this implies, so I have x square, yeah, and x square plus 1, right? How many choices will be there? So for a0, a1, 2 to 2, total 4 choices are there, correct? So can somebody tell me other x square plus x plus 1, what is missing? X square plus x, correct? These are the 4 polynomials of degree 2, right? Now out of these, how many of them are irreducible, correct? Yeah. So x square is equal to x into x. Yeah. X square plus x is equal to x into x plus 1. Sorry, x square plus x. What about x square plus 1? Yeah. So can I ask? Can I ask one person? Okay, Suresh, can you help me? How do you write x square plus 1 as product of
X plus I, x minus I, but in real there is no irreducible polynomial.
but here f2, I am working in f2. What is f2? Z2. Z2 means 0, comma 1.
Yes.
Okay, I'll help you one thing. So to make it, so see what is happening is that I take any field, let f be a field. I'll ask few questions. Let f be a field and I take a linear polynomial. Ax plus b belong to fx, right? So then can you tell me the root of this polynomial?
Minus b by a.
Yeah. Then root of ax plus b is minus b by a, correct? Is it belong to f?
Yes, sir.
Yes. Why it belongs to f? Because f is a field. So actually I should not write like this because I don't know. So what is that I write here? Minus a inverse into b, correct? Since f is field, and so a inverse belongs to f. Okay, so minus a inverse into b belongs to f. So what is that we proved? For example, be careful here. For example, 2x plus 3 belong to zx. But what is the root of what is root of 2x plus 3? That is minus 3 by 2. But this does not belong to z. Are you following that?
Yes, sir.
Yeah. So what is the conclusion now? Conclusion is that every linear polynomial, over f has a root in f itself, right? Yeah. So now what is the question? If f of x is a if f of x belongs to fx, is of degree 2 or 3, then fx is irreducible if and only if. So Achila, Kanak, any one of you, can you say something? F belongs to fx is of degree 2 or 3, then fx is irreducible, reducible, better say reducible. Yeah. If and only any one of you, please help me. Is of degree 2 or 3, then fx is reducible if and only if. Okay, what do you mean by reducible? Okay, I'll help you. Suppose fx is reducible. What do you mean by that? Yeah, can somebody help me? At least this part. I think I am not audible, right?
There exists g of x and h of x in fx.
G of x and h of x in fx. Yeah, such
So
that.
that f of x is equal to g into h.
Yeah, g of x into h of x. Yeah, but now, and also we need to tell much more that degree of g comma degree of h is greater than or equal to 1 hours. Correct?
Yes, sir.
They are 0, it will not. They become units. So reducible means I can write as a product of two non-units, right? Yes. Okay. So this also part and parcel. Okay. Now come to the question. If what is that I have to write here? Yeah. So now I'll write one more step here so that now we can fill up this. Now degree of degree of f is equal to 2 or 3, right? And also in the vectors, even in IDs, we have this degree of fx equal to degree of g plus degree of h. Do you know that? I can prove if you want, but this we have. Yeah. Now my degree of fx equal to 2 or 3. Now can you fill up this? And I proved this. Every linear polynomial over f has a root in it. By combining these two, can you say something here? Reducible. Okay, still you are not able.
One of G and H must be linear.
So one of G and H may be linear. But when we have a linear, then you know something. Every linear polynomial over f has a root in f. And yeah, so here this implies that, so here 2 or 3, right, is equal to degree of this, right? So this implies you are correct. This implies what? This implies degree of g of x or degree of h of x is 1. Is 1, right? Yeah. So from that, what to conclude now? Fx is irreducible if and only if
It has a linear factor.
that is okay. Having linear factor now is same as
Uh,
root in f, right? Fx has root in f. Thanks, actually. You can prove both the sides. See, for example, f has a root. Okay, alpha is a root in f. Then how do I write fx equal to x minus alpha into something? You agree with me? Hannah?
yes, sir.
So it is actually product of x minus alpha into something that is reducible. If it is reducible, then one of the factor is degree 1, but that has a root in f itself. So fx has a root in f. So if your alpha is a root for g, it is also root for f, right? So why I'm telling this particular thing, this is very beautiful part. So to check given polynomial is reducible or irreducible, it is sufficient to check it has a root in f. But this work only for degree 2 or 3. See, so conclusion, moral is that, so to check fx belong to fx of degree 3, of degree less than or equal to 3 is irreducible degree 2 or 3 better, 1 anyhow irreducible है. If and only f has no root. Yeah, otherwise fx is reducible if and only f has root in f. Okay, so what about x square plus 1 over r? Irreducible. Why? The roots of x square plus 1 does not belong to r, right? Yeah. So, but if I take any polynomial of degree 3 in Rx, what do you say?
Will be reducible.
Why it is
Yes.
reducible? Yes,
We
correct.
have 3 roots. two of them will be complex, the other one will be real.
It's always. So in particular, can you extend this result? If I take any polynomial of r degree,
Then it must be reducible over Rx.
yeah, so it is always has one real root, right? Yeah, but one thing I want to tell here is that, see, x square plus 1 power square, right? It is equal to x square plus 1 into x square plus 1. Simple example, right? Which is equal to x power 4 plus 2x square plus 1, right? So is it has any root in Rx? Has no root in Rx. But is it reducible or irreducible?
Reducible.
But reducible, right? But reducible. So be careful. 4 onwards we can't say. 4 onwards it will not work. Yeah, 4 onwards that will not work. This will work only when degree 2 or 3. Why I am telling all these things? Now I am going to Suresh again. Right? So x square plus 1 is reducible or irreducible over Z2. So how do you check? So if it is reducible, then what is going to happen? It has a root. If it is irreducible, it has no root. But what are the elements in F2? Luckily, there are only 2 roots, right? Only 2 elements in F2. Any one of them is satisfying here?
X equal to 1.
If I substitute 1, automatically it becomes 0, right? So 1 is always a root. So it is actually x plus 1 into I have to do something, right? Can you tell me what is that other one? But it has one root, then it is other root also. What is other root? But there are only 2 elements, 0 and 1. So that means both the roots are same. So it has a repeated root, yeah, in F2, right? That is what you know. So 2 is equal to 1 square plus 1 square, right? So it is equal to 1 plus I into 1 minus I, correct? All these things, Gaussian integers, everything, it's okay. But why it is happening like this? Actually, x plus 1 whole square is x square plus 2x plus 1. But the f is a characteristic 2, so this becomes 0, right? So it is reducible. Is it okay, Suresh, now?
Yes, sir.
Yeah, good. So it is reducible. So in particular, somebody can help me that I gave a polynomial fx with even number of terms. Even number of terms. Then what we can say? Even number of terms. Terms are even. Then what we can say? What we can say about f of 1?
Will be 0.
0, right? Because I'm substituting 1. How many are there? 1 plus 1 plus 1 plus 1 plus n even number of times. So it is equal to 0. So it is never be reducible. Irreducible. It is always reducible. So in F2, you take any polynomial of degree, even degree, then it is not even degree, sorry. Even number of terms, then it is reducible. Okay. So it need to have, I'm not telling the degree, I'm telling about number of terms. Yeah. So now look at x square plus x plus 1. Now it is easy now for you. It is a polynomial of degree 2. So it is reducible, irreducible depending upon the roots. But now I'll substitute 0, not satisfying. 1 also I substitute, not satisfying. So what is happening? This x square plus x plus 1 is irreducible. Are you now clear?
Yes, sir.
Yeah. Okay. So summarize once. Okay. Summarize once one more time. So over F2, polynomials of degree 1 which are irreducible are x comma x plus 1. Don't worry that x minus 1 is equal to x plus 1. Yeah. Degree 2, which are irreducible polynomials. Degree 2, what are all polynomials, right? See, look at this x square, which is equal to x into x, but this x coming from here, x square minus x or x square plus x, so which is equal to x into x plus 1, product of these two together, right? X square plus 1, which is equal to x plus 1 whole square. See, it is x into x came here, x into x plus 1 here, x plus 1 whole square here, right? That is quite obvious, right? These are two linear polynomials, so I can multiply to itself or product. I'll get three polynomials of degree 2, right? These are all three came. Now one is missing, that is x square plus x plus 1, right? So now multiply these three and look at what is going to happen. We'll multiply these three, x and x minus 1 into x square plus x plus 1. Can somebody tell me what is the product of these three? Easy. It is x power 4. Why you are not telling? Product of these two is x cube minus 1 multiplied by x. Okay, anyhow, I am telling x power 4 minus x. But you know that there is a splitting field, right? X power 4 minus x. What is the field? Can you somebody tell me? What is splitting field for x power 4 minus x? Okay, I'll write it. This is 2 square minus x. Somebody help me. What is the splitting field for this? How do you? That is unique, and we told that. What is that? F for 2 square. Yeah. So how the splitting field came now? It is a product of the f2 square minus x. Actually, this, look at this 2, right? So it is a product of all polynomials of degree 2 or 1 less than or equal to 2. Okay, it is very interesting. We go further. Let us work out now degree 3. Degree 3 irreducible polynomial. Somebody can help me now? Okay, again try to write a0 plus a1x plus a2x square plus a3x cube. So these are the polynomials of degree 3. Total how many will be there? Total 8 are there, correct? Am I
16.
doing 16? Yeah.
Sorry, 8, but because A3 has to be 1, so 8.
Yeah, 8 because yes, a3 is equal to 1. I'm also confused. Yeah. Okay. A3 is equal to 1. So what are the polynomials, right? So first thing is that I take a0 equal to 0. Okay. And then I'll get so x cube is 1, right? And x cube plus x square is 1, right? X cube plus x is 1, right? X cube plus x square plus x is 1, right? Okay, let us write orderly fashion. Is it okay? Is it clear to all of you? Yeah, now a0 is not equal to 0. That means 1, right? No need to write not equal to 0, equal to 1, right? Which is equal to 1. Yeah. Now what are the polynomials, right? So again x cube plus 1, right? X cube plus x cube plus x square. Oh, I done a mistake, huh? Plus 1 is there. X cube plus x square plus x plus 1, right? Now, so what about these polynomials, Suresh?
Reducible.
Reducible. Wonderful. Why they are reducible? Because I can take x outside, right? X into something, correct?
Yes, sir.
Yeah. Otherwise, what is other way to tell? All of them has roots in F2. Which is the root?
0 or 1 is root.
0 is a root. Why?
Yes, sir.
Or 1,
Sorry,
0 is a root.
sorry, 0 root.
0 is a root for all of them, so we are done. So it is reducible. Because degree 3 or degree 2, if it has a root, then I am done. It is reducible. If and only, yeah. What about this?
1 is root. Yeah,
Why
x
1 is a root?
sorry.
Why 1 is a root?
So 1 plus 1.
Yeah, but it's okay. But can you tell me more better way? These two together, one shot. Both of them, of course, one satisfy, right? Here also one satisfy, right? Okay. Why the one satisfying both of them? Can you give me common reason? Yeah. Anyone else?
Even number?
Even number of terms. This has 2 terms, this has 4 terms. So when I substitute 1, 4 times I'm adding 1, or 2 times I'm adding 1. So 1 is a root. Yeah. And so what are the irreducible polynomials now of degree 3 over F2? X cube plus x plus 1 and x cube plus x square plus 1. So these two polynomials are of degree 3 and irreducible. Degree 3 irreducible, right? Now I'll multiply all of the polynomials. So x into x minus 1 into x square plus x plus 1 into x cube plus x plus 1 into x cube plus x square plus 1. Can you predict what is that I'm going to get? So see,
X
this is,
raised to 8 minus x.
oh, wonderful. X power 8 minus x. How do you came to know that? You are correct, but how do you got it? So this is related to f2 power 3, correct? Yeah, so actually this is isomorphic to f2 of x, ideal generated by, so any of these two degree polynomials, right? So finally, what is it we are doing is that, so if you go like that, you can show that for any given n, there is an irreducible polynomial of that degree. So that way also you can prove that there exists a finite field with p power n elements. Yeah. Yeah. So try to figure out degree 4 polynomials also later. Yeah. So I will stop here. And I'm extremely sorry that today I delayed a little bit.